Um, we are looking at the 2008 AP Physics C Mechanics free response question number 2. It is a torque problem and a little bit of angular rotation. What we have here is a horizontal uniform rod kind of cutting across to the center there. And this rod has a length of 0.6 meters and a mass of 2 kilograms. So that's nice for us. The left end of the rod is attached to a vertical support. So there's a vertical support by a frictionless hinge. That's nice. That allows the rod to swing up and down. The right end of the rod is supported by a cord that makes an angle of 30 degrees with the rod. And a spring scale of negligible mass, so we don't have to worry about its mass, measures the tension in the cord. A half-kilogram block is attached to the end of the rod. On the diagram below, we are just labeling all the vectors to represent all the forces acting on the rod, show each force vector originating at its point of application. So we're drawing a force diagram, not a free body, but a force diagram. When we draw this, we just need to draw the forces. We are not drawing their components. So the first thing that we can do here, if we take a look at some of the things going on, is we know that we've got a mass out at the end pulling down with its weight, which is mg. We also know that we have the rod itself trying to fall. If the rod just existed and we let go of it, it would just fall under its own weight. So it has a weight vector here, mg. We also know that this string attached to the spring scale is trying to pull this rod like back. So this spring is pulling back this way with some amount. We don't know what that amount is, so it's just some tension there. And because this is in a static equilibrium, it's not rotating or moving at all, I know that there needs to be another force. Maybe this tension is holding up all the way, but this tension is pulling a little bit to the left. And since this tension is pulling a little bit to the left, something needs to be pushing back to the right in order for this to not be moving along or be rotating. And the thing that's actually moving back to the right is the hinge. It's pushing back to the right. So this hinge could be pushing just to the right, but in reality, this hinge is going to be pushing to the right and up by some amount. It has to push to the right by some amount in order to equal out the tension force pushing to the left by some amount. And more than likely that tension force isn't holding up the entirety of that weight. The hinge is doing some of that work there too. So those are our 4 forces, and that's that. 1, 2, 3, 4. That's all that's going on. It's just important to remember that we start these vectors on the diagram. Some people, when they're getting lazy, they'll just like put it off into space like that. Don't do that. But not too bad there. Now what we have to do is we have to calculate the reading on the spring scale. And when they're asking us to calculate the reading on the spring scale, what they're really asking us to calculate is the tension itself. So in order to do this, we need to set the torques equal to 0 because this is in a static equilibrium. And to do that, if we set the sum of the torques equal to 0, remember that a torque by itself is equal to some moment arm times the force being felt, which is actually what we're looking for, times the sine of some angle between them. And when we look for the sine of those angles, we'll talk about that and how to find them. But we have, in this case, we need to pick a pivot point. The pivot point we're going to pick here, we can pick anywhere, but we're going to pick the hinge. What that does is it will actually eliminate one of our forces that we have here, one of our torques. So we no longer have to really worry about the hinge because the hinge is at that position there. So we don't have to worry about it at all. When we go ahead and look at our torques then, to set them up equal to 0, we have the weight of the rod. And it is a distance away from the hinge itself. Since the rod was 0.6 meters, this distance is 0.3. So we can say for the rod, it's going to be 0.3 times mg. And if we were to shift this weight vector over to the pivot point, we'd see that we have, I'll erase this because that's a part of that problem. We'd see that if r is going this way, mg would be acting like this, and then the angle from our moment arm to the force is this, which is clearly 90 degrees for us. So what we would put in here is we would put in a sine of 90 degrees, but we know the sine of 90 is just 1, so we don't actually need it. We would add to this the next pieces. At a distance of 0.6 is the mass itself, mg. It's also a sine 90, so we won't have to put anything. And what I am doing here, and this is really depending on how you just feel about things, I am calling objects that are rotating the rod in this direction, I'm calling that positive. You could call that negative if you want. There's nothing wrong with that. You just need to pick a direction. I just started with those being positive, and I'm going to keep it that way. A quick way to just see if, you know, how an object is rotating the rod is if you just take the pencil in your hand or whatever, and you just stick your fingers on one side of it, then you can see just by saying, look, I'm pulling down here, which way is this rotating? You can get an idea of how forces are rotating your object. So just keep that in mind if you're getting stuck in a problem. Just start holding things, look like a fool during the test, but you're going to get it right. Last but not least, we need to look at this tension force from the spring scale itself. If we take a look at this, this is going to be rotating it up this way, which we need to call this a negative value. So we'll say minus. It's still 0.6 meters away. There's the tension. And because it's at some angle, it's not 90, we need to figure out what it is. I'm going to sneeze. Whoa, where did that come from? Oh, boy. So to figure out what that angle is, if we drew the moment arm, this tension is coming back like this here. So we want the shortest possible angle from the moment arm to the tension. In the problem, they give us that this angle is 30, which is going to make this angle out here 150 degrees. Okay, so it'll be sine of 150 degrees technically. Great thing for us is that sine, as long as we're choosing the smallest angle, it'll always be in the first and second quadrants, so it'll always be positive, which means you need to be careful about that. At this point, it's just a matter of trying to figure out what's going on here. So let's see what we've got. Time for some math. This is gonna be good fun. Let's do the math down here. We've got 0.3 mg plus, actually, did they give us? Yeah. Plus 0.6 little mg minus, what's the sine of 150? Sine of 150 is like the sine of 30. Sine of 30 is, oh, I should know that off the top of my head. Is that a square root of 3 thing? No, it's just 0.5. Oh, we've been doing that all day. So sine of that is 0.5. So we're going to get 0.3 times t over here. And then, do we have masses of things? We do indeed. We know that this mass is 2. We know that this mass is 0.5. So we're going to get, and so all of this equals 0. So then what we're going to get here is, still solving this out, 0.6 g plus 0.3 g equals 0.3 t. That's going to give us 0.3 g plus g equals t. Is that right? I think I just messed something up. Oh my goodness. 1.3 times 9.8. Yeah, that's only 12. What did I botch here? Ugh, I'm having such a bad day with this. What did I botch? That's 2. That's 0.6. That's 0.3. Where did I divide wrong? The 0.3 dividing by point. Oh, jeez. 0.6 over 0.3 isn't 0.3. What am I doing? This is 2. This is 2g. Ugh. It's 3g. What a morning. What a morning. It's about 30. Right? Yeah. Newtons. Is that it, Wild Bryant? Thank you for that. Rotational inertia about its center. Okay, so let's do part B. What am I looking for? Calculating the rotational inertia. Calculating the rotational inertia of the rod block system about the hinge. Okay, so we know the rotational inertia of the rod about the center is 1/12. So this actually starts to apply what's known as the parallel axis theorem. Let's draw the rod again. What they're saying is that if we put a hinge at the center here and then rotate this, it has a moment of inertia I of 1/12 ml squared. In order to find what the moment of inertia would be at a different position, some position that isn't through the center of mass but is offset by some distance, r or l or whatever you like to call it, all you have to do is you have to add the original moment of inertia to this mr squared value. Okay, this is what is known as the parallel axis theorem. So in our case here, we've got 1/12 ml squared, and then plus the mass of our rod again, and then this distance to an edge, which is actually just L over 2, but we need to square it. So what we're going to get here is we're going to get 1/12 ml squared plus 1/4 ml squared. And this means we have to do some fractional math, which is always fun. Learn your frog fractions, children. Let's see. 1/4 is the same as saying 3 over 12, and 1/12 plus 3/12 is 4/12, which is the same as saying this is 1/3 ml squared. Ugh, math. Okay, this parallel axis theorem idea, though, you're always just adding some offset position. That's a very, very important thing there. I don't know if you do that often in Physics 1. See you, Dodo. But that's what's going on there. It's a parallel axis theorem problem. If the cord that supports the rod is cut near the end of the rod, let's say it's cut perfectly, there's no like snagging, calculate the initial angular acceleration of the rod block system about the hinge. So what's going to be going on here is we can say that the sum of the torques at this point are equal to I alpha. So the sum of whatever torques we have are going to equal to the moment of inertia about the hinge, which we just solved for up here. That, multiplied by the angular acceleration at that point. So if here's once again our rod, Here is our hinge at the end. The only two forces we're going to have now are the mass of the rod and the weight, or rather the weight of the rod, excuse me, and then the weight of the small mass at the end. We'll say that both of these are turning it this way, which will be positive, just to make life a little bit easier. So all we have to say here is that our torques, which are, once again, a radial distance, a moment arm, times the force, that will be a radial distance of 0.3 in order to get to the center here, times mg, plus, because we're rotating it in the same direction, 0.6 times little mg. That's going to equal 1/3, and then what am I looking at this first one? Oh, you know what? I just realized something. I don't want that third. That third's no good to me. This 1/3 ml squared is just the rod. This is just the rod at the hinge. If you want to find the total moment of inertia, you have to take the rod at the hinge and you have to add to it the moment of inertia of the point mass sitting out at the end. Which is the small mass we're putting onto the outside. So what we're going to have here is the total moment of inertia is going to be the 1/3 rod L squared plus, and then the moment of inertia of the point mass we're adding on is just mr squared. So this is going to be the small little mass times the length of the rod squared, because that's where it's at. And if we do this, we're going to get 1/3 times, oh, what's the mass of the rod again? I can't remember this stuff. Times 2 times 0.6 squared plus 0.5 times 0.6 squared. That's what we want. This is the total moment of inertia. Let's just crush this number. 0.6 squared times 2 divided by 3 plus the quantity of 0.6 squared times 0.5, 0.42. So this gives us 0.42, and that's always mass kilograms by distance meters squared. Okay, that's what we want. Got to remember that second part here. That's huge. So now when we come down here, this moment of inertia is going to be the total moment of inertia, which is the 0.42 we just found, times the angular acceleration. So now we can go ahead and solve this. Now we can say that, looking right here, we're going to get 0.3 times 2 times our 9.8 for gravity, which we could just say is 10, but whatever, plus 0.6 times 0.5 times the 9.8, all divided by the 0.42. That is going to be equal to alpha, which, oh boy, let's see. 0.3 times 2 times 9.8 equals plus the quantity of 0.6 times 0.5 times 9.8 divided by 0.42, about 21. Actually, I got exactly 21, which is cool. And units of alpha are angle, which is radians, per second squared, because it's an acceleration. Okay, so that wasn't that bad. I just had to make sure I got that correct from part B. If you had that part wrong from part B, you'd probably get a consistency point there. Is that it? Is that my problem? Oh yeah, because this is mislabeled. A. Okay, so that's it. That's the problem. Nothing too crazy there. You actually got 4 points right in the beginning just for this picture here. In part B, you got a nice 4 points for setting up the torques. As Wild Bryant has pointed out, be careful with your division. I botched that right there. And then, so that's 8 of the 15 points. The last points came in part C, which was 3 points here. This is probably actually the hardest part because you had to use the parallel axis theorem, and then, like I almost forgot, you have to add on the extra mass at the end, which acts as a point mass, which is just mr squared, and then you can go down and do another torque problem there. So nothing too busy. Almost caught us up a few times though, but in the end it is finished. Man, what a rough morning. Take it easy.